Okay, let's go on. Now we are going to have a bit more detailed view about a particular kind of graphical models, which is the so-called hidden Markov models. They usually handled separately because they address a certain kind of problem. They have been used very often already in the literature. They're kind of important for many kinds of reasoning tasks. And we can see a lot of these general algorithms that we had, or the general algorithm that we had so far, in a particular setting of hidden Markov models. I think this makes a little more sense then to understand about these reasoning algorithms. So first of all, let's go back again into our very first lesson. We had this kind of graphical representation. We had some states here, we had some observations, and we had some actions. And of course, we have here the t value is the time step. So that means that for every time step we have a state in which we are, and this state is unobserved. We don't know in which state we are. We have some kind of input values here, and we have some kind of observations here. And we have these Markov assumptions that things are independent. The measurement only depends on the current state, and the current state only depends on the previous action and the previous and the current action, right? UT and previous state. So for Markov random fields, for hidden Markov models, we assume we don't have any actions, right? We only have states and we have observations, which makes things a bit easier. Now we only have these two formulae here, right? Which are a bit simpler. One note here, in this lecture here, I will have a slightly different notation, which might be a little confusing. Actually, it's for me myself, it's very confusing because when I prepare the slides, I take, of course, the book, and this has some historical reasons, and at some point I should probably change that. But for the moment, I couldn't do this so far. The reason for this is that this is the robotics way to write the things, right? In robotics, a state is always denoted as x, and observation is always a z. And in machine learning, it's actually exactly the opposite. So it's really bad, right? I apologize for that. I hope you can kind of understand the difference here and still be able to understand what's going on here. So as I said, I might be able to have some time to really change all these now on all the slides, but it's a bit, can imagine I have to take them all again. So yeah, so let's say first we have states and we have observations, and to start we take a simple example. And this example is taken from Murphy's book. So in this example we have the so-called occasionally dishonest casino. And what this means is we have two dice, and one of the dice is fair and the other dice is loaded, it's unfair. And the problem is that we never know which dice is actually used from the casino. The casino just changes the dices, and we never know which dice they actually use. The only thing we have is observations. So we have these z values, which are discrete states, right? We can have a state from 1 to 6. And we have this kind of data here. So we have rolls, this is what we observe, and these are the hidden states which we don't observe, right? This is the actual dice that we use, right? This is the loaded one, and this is the fair one. Loaded, fair, fair, loaded, loaded, fair, fair. And now the problem is, can we have some kind of reasoning? Can we, only by observing this data, infer which kind of die we're actually using, right? And this is the kind of problem that we can solve with HMMs, with hidden Markov models. The state transition diagram is this here. I think we had this already. So we have two states, which is the fair die, and this is the unfair. And there's some probability to change from one to the other. So this is something we have to either learn from data, or we, for the moment, assume that we know these transition probabilities. We know that if we in this state, if we have this die, then it's very likely that we take the same again. With some slight probability, we change to the other one. But once we're in this state, we stay for that for a long time, right? We stay there very, very likely. And then eventually, we go back into the other one, right? This is the probability table for the two states that we have here. Now let's formulate that with an HMM. An HMM in general has, first of all, some discrete random variables. These are the observations, Zn. where n is goes over all different goes in time over different observations. Then we have state variables. These are the xn. These are not observed, right? This is what we want to reason on. We'd like to know that for something from the data. And we have a number of states. So we have k. This is the number of given states that we have in our model. So for this very simple example, k is equal to 2, right? We have 2 states, and xn is a discrete variable that just takes probabilities over these 2 states. Then what we need is, of course, this transition model. This is what we had here, right? This is what's the probability to change from one state to the other state. This is denoted as this here. So we have a conditional distribution, a conditional probability of being in one state given I was in another state the step before, right? These indices here are time steps, are steps in time. So that means if I have been in this state before, what is the probability to be in this state now? These are the transition probabilities. Of course, we have the Markov assumption. Otherwise, this would not make sense to call this a hidden Markov model. So this is the reason why we call this Markov model. That means that the current state only depends on the previous state. We can represent this transition model as a matrix, right? We have a k by k transition matrix because we have all discrete variables. We have just fill in the probabilities of these transitions. And we have an initial probability. This is something that we have to kind of also model, right? We have to know what's the initial prior probability to reach any of these states, right? If we have a number of states, for every state we need to know how likely is it that I start in that state. In the easiest case, I can just say this is the uniform distribution. Every state has the same the same probability. Now, the observation model is this here, right? This is what we in robotics call the sensor model. So if we have a state here, then what is the probability of observing a z value in that given state? And this observation model has parameters phi, and and again, this observation only depends on the current state, and the output is a local place classifier. Well, let's go on. The interesting thing here now is to note that the whole model is parameterized by these things here. So we need to specify A, we need to specify these pi's, right, the initial probabilities, and the parameter of our observation model. Now, the whole thing is much more easy if we look at this representation here. And this is called a trellis. The trellis is a kind of graphical structure which is not the same as a graphical model. This is a very important thing here, because these nodes in this graph here, they don't represent variables, they represent states of variables. So that means that every column in this trellis graph here corresponds to a variable, and every variable has a number of states. In this case, we have 3 states. And I think what I should do is, to do this later, I just copy that here, because then I can later more easily explain things with this graph, right? So we have these 3 states, right? For the moment it's 3, it's easier to do that. And every column is a state, is a variable, and variables are indexed by time, right? So n, if we say n minus 2, n minus 1, and n, then in the most general case, I can travel from every state to every other state. Oh, sorry, I had that already. So that means there is these transition probabilities between the states, and I think I have them all right. Oh, this one is missing. And so on, right? Now, what's missing here, of course, is the observations, right? We only have the states, x, and we're missing the z's here. We could do that by simply adding to every state an observation, right? Z, n minus 1, minus 2, 1, and so on, right? Which then means if I'm in this state here, then I can observe this. if I'm in this state, I can observe this, and if I'm in this state, I can observe this. For every state, I can have a different observation. Now, let's look at an example where how this looks like, like in a formulation here. Now we're given a sequence of observations. First of all, we assume that we know all the models. We know all these probabilities here, the transitions between the states. We know the initial states, which are these pi's, right? If you think that this is the first thing, and we say pi 1 is this and pi 2 is this, just the probability of reaching that state, right, before seeing any data. And phi is just the probability, the parameter that gives us a distribution from observing something in a given state, right? This is phi. And we assume that we know all that. Now, the first question we can ask is, what is the probability that the given observation sequence is actually observed under this model? That means we have a certain observation here, which we can probably call, we have here z1 n minus 2, z n minus 1, z n. And these are the actual observations that we get from data, right? We can really write numbers here, right? For our case of the dice, we can just say this is 6, 5, and 2, and whatever, 1, whatever, right? So, and now what we like to know is how likely is that actually? So, what is the probability that we actually observe that given our model? Now, if we're given 7 different models, that the idea here is then, we could train different kind of models here with data where we have different parameters here, A and P. And for every of these models, we can then choose the one with the highest probability. This is the idea, right? We'd have an HMM for all kinds of classes, and then we take the one that is most likely. Yeah. Now another example is, again, we assume that we know all the parameters, but would like to not only know how likely is it that we observed what we actually observed, but also what's the most likely sequence that we take to observe that, right? Which is much more interesting, right? We'd like to know which were the dice, the kind of dice that we used to create this observation sequence, most likely, right? Yeah, this is an old thing here. I have to remove this. For place recognition, you can use that, but we're using now a different example. And finally, the third application that we can do with HMMs is completely different. So we're given an observation sequence again, but now we don't know the parameters of the model, right? And we have to learn them from data. And this is done in a training step, right? This is generally the most difficult problem. But for all these kind of 3 problems that we have, there are algorithms that I would like to present now in a bit more detail. To summarize, we have these 3 operations. The first thing is just compute the so-called data likelihood, right? We are given the model. The model is now just one notion, right? This theta here is just these 3 parameters here, A, pi, and phi. They're all got together, or grouped together into one variable, which is just the number of, or just the parameters of our model. Once we know the parameters of the model, we'd like to know what's the probability of what we actually measured, right? How likely is it that we measure what we actually measured? Data likelihood. This can be computed with the so-called forward-backward algorithm. Then to compute the optimal state sequence, which is also very interesting, right? We would like to have the xn, so the sequence of x1 to x big N, which maximizes the probability of our observation, right? This is can be done with the so-called Viterbi algorithm. And finally, to find these parameters here, A and pi and phi, what we can do is we can apply the so-called expectation maximization algorithm, or for the case of HMMs, this is called the Baum-Welch algorithm. So let's go step by step through these algorithms. The first one is the so-called data likelihood. So now we assume that we have this state sequence, right? And we know that now, right? Is that right? Yes. Now, if we know that, then we can compute there's 2 operations that we can do now. We can compute we can filter this. We can use filtering, is it called? This means that we compute just for every state. We compute the probability that we observed that, right? It's the state probability only based on previous observations. I think this is again. Yeah, no, that's right. That's right. So we have up till t. Sorry, I think this is another thing that is kind of misleading. These n's here are actually t's, right? This is again the reason why. So in one book it's named t, and the other book is n. And if you use two books, then it's a pain. T, right? So so this is the filtering part, and you could also do that not only based on the previous observations. You could also do that for all observations. This is called smoothing. The difference here is simply that for filtering, you only look at the observations that you had so far until t, right? You interpret this as a time sequence. For every time step, you have observations, and you just compute the state at time xt given all the observations so far. Smoothing, however, does it a bit different. Smoothing waits until it has observed everything, right, until capital T, and then does a reasoning backwards, right? It then says, in hindsight, the most likely state, or the most likely, or the probability of my observation is like that because I know now more things, right? This is kind of interesting, right? Because for the smoothing, you have to wait until you have observed all the data. But then, once you have observed all data, you can then go back and update your model, right? And find better probabilities here that explain your observations better. And this is just an example how this looks like. So at filtering, there's a reason why it's called smoothing. Filtering, you have a very highly changing function here. What this plots here is this is actually our example with the two dice, and the blue curve here represents the probability of having I think it's the unfair dice, right? The loaded dice. That means in gray this is the ground truth. So we know wherever there's this gray area, we actually used the loaded dice. Right, and our model estimates this function here, right? It estimates something. You can think of there's a probability, of course. You can threshold this and say, hey, give me all the states, all the states where you think that it was the loaded dice, and then you would have all these here, which are higher than 0.5, right? And in many cases, it's actually right? But in many other cases, it's probably not so right. And smoothing does this a bit more clever, let's say, right? It has more information because it has looked into the future, and then goes back and does a reasoning which is much smoother. Right? This curve is much smoother, and if you think now, if you threshold here, then you say in every time step you can then compute find the most likely state with the smoothing. Now for filtering, to do filtering, we can do the so-called forward algorithm, and to do that, we first compute the prediction from the last time step. But what this means is I have observations from the time step so far, and I would like to find what's the probability of being in state j at time t, right, given all my previous observations. And to do that, I simply sum up over all possible states that I could have been in that previous state, right, and multiply that with the transition from that state into the current state. This is exactly what we do. The whole thing is exactly what we did in the base filtering in the very first lesson, right? This is just two things applied to it. This is just the law of total probability. We just say, what are the possible states that I could have been before, and could have been before this current state? This is this here, and for every of these, for each of these states that I could have been, I need to multiply that with the probability of switching from that state to the current state, right? And I marginalize that out, which is the same as here, right? So I can compute that easily by just summing up, right? And now what I can do is I can denote this thing as an alpha, right? This is my alpha definition. I say This term is alpha, which is exactly the same. Now I split this Z1 to T, I split this up into the last observation and all the rest of the observations. And now I apply Bayes' rule, the same as before, as I had this in the first lesson. So I turn these two things around. I say xt equals j goes to the right, and zt goes to the left. I switch these two things. But to be able to do that, I have to, of course, also multiply with the prior in this case, right? It's the prior on our state, and I have to normalize, right? I have to divide this with zt, which is simply the sum of all these kind of things of the states. So this is just applying Bayes' rule in a very simple fashion, right? Right. So again, I have found a formulation of a particular application of the Bayes filter to estimate these probabilities here, right? To estimate state probabilities given observations. This thing here cancels out because this is the Markov assumption, right? I assume that I only need to know the current state to be able to know what kind of observation I have in the state. I don't need all the previous observations. I think this shows it again, right? We have here our observations, our state sequence and observations, and our alpha is simply now for every state the probability of observing everything that I have observed, given that I'm the probability of being in that state given all the observations before that. The same thing we can do now for beta. Beta is now a distribution or a probability that reasons on the future, right? This thing here says, given I am in this state here at time t, what is the probability of observing my z values, where z is the actual observations, right? This is what I know, and this is what I don't know. I don't know which state I am, but I know what I have observed, right? So given xt equals j, what's the probability of observing all these zt's? And beta can again be computed recursively. Yeah, but we do this in this way here. So again, we do we sum over all states, right? This is just marginalization applied the opposite way. So we just go, we add something to it and marginalize it out again, right? This is just all possible states xt. Now we have j here, so we have now two states. We have xt and xt minus 1, right? We have to say now beta goes now from right to left, right? Now beta t minus 1 is the next in the sense of beta, but of course it's previous compared to beta t, right? So what we actually, we express beta t minus 1 as beta t, where beta t is of course the next step in time, but we reason backwards, right? This is the the whole thing of these betas here, right? Beta t minus 1 is computed recursively from beta t. And this whole thing is, again, very simple, right? We have again here the Markov assumption. These things cancel out because I know that I only need to reason on the state. Given if I know the state, then all the rest is not interesting to me anymore. This thing here is also, again, marginalization. So we put a new variable, where is it? Here, this xt minus, sorry, where is it? I think this part here, this term here is again split up into a part where we just reason on the state and a part where we reason on the observations given the state, right? This is just again plugging in the rules for probabilities, right? Conditional probabilities. So this joint here, given something, is nothing else than this part times this part given the other one, right? This is A and B equals A times B given A, right? This is just nothing new here. And now we can again cancel out this here because now again we say zt only depends on xt. Xt minus 1 is uninteresting. So we have this kind of simpler formula here, right? And the whole thing is that this front part here, this front term, is nothing else than the beta that we already have, right? This is now the interesting thing about this. Alpha and beta are now again messages, right? This is the message passing algorithm just applied to HMMs, right? Alpha is a vector of discrete states. For every state in this vector, we have a probability. So the distribution, we write this as a distribution. In the end, it's just a number of values that tell me for every state what is the probability of that state. And the same for beta, right? For every state at time t, right? For this j here is just a value that goes through all the states. And for every state, we have a probability, and all these probabilities are then together they form a distribution, right? So, and that's the interesting thing, right? You can now compute this recursively again, as we did this before. The betas are just messages that go from right to left, right? They go backwards in time, and alpha goes forwards in time. And this is the reason why this is called the forward-backward algorithm, which is nothing else than some product, right? We just had that already, right? We just have to represent alpha and beta as messages. Alpha t is a vector of length k, which is just, right, this thing here, and in the end, it's nothing else than multiplying alpha with beta, right? So if you, where's the definition of alpha and beta? It's here, right? If you imagine this thing times this thing is exactly what we need. This is exactly our probability of observations, right? This is what we want to have, right? How likely is it that we observe that? Yeah. Now the second problem that we would like to address with HMMs is these computing the most likely states. And there, I think we had this already. This is the max product or max sum algorithm that we had in the previous lesson, just applied to HMMs, right? The idea is probably the same as before. Instead of summing up things, we take the maximum of it, right? We don't do a sum over all possible states of X. We do a maximum of these. And yeah, so the way this works is probably easily shown in the trellis representation. So first of all, we define these delta values here. Delta is just the maximum over all paths. Paths means sequence of states, right? X are states. So the sequence of all states, and we'd like to find the over all these states the maximum probability of these sequence of states and the current state given all the observations, right? So we put ourselves in this position here. We are here. We condition on all the observations, and we'd like to find the path that maximizes this probability, right? Which is what is the most likely state sequence that created our data. Now again, we can complete this recursively, and this is how it looks in math. In the graph, it looks like this here. We are the current state here, and for every state, we would like to find the maximum path that reached that state. And the assumption is that for all previous states, we know this already. We know which path was most likely to reach that state, right? So the path means just hops in this thing, right? A path is, for example, this is one path, this is one path, and this is one path. So if we have all these states here, we assume that we know how to reach that state with the most likely path. The only thing you have to do now is, for every new state, we have to multiply the probability of reaching that state with the probability of jumping into that state, right? So we say, what's probability of reaching that state times the probability of going into that state, times, of course, which we never should forget here, times, of course, observations, right? We have, of course, observations here. So for each of these states, we have, again, observations, so we have to multiply that again, right? And this is our sensor model, which we assume to know, right? We know how likely is it to observe this Z value given we are in the state. This is the last term here. And this is our state sequence, our state transition, right? So again, we have this in a recursive way. Important part here is that we not only have to compute the probability itself of our maximum path, but also we have to remember where we came from. We have to also remember the state that created that maximum. So if we compute delta for this state here, right? This is delta. Let's say this would be delta t of 1, right? This is our state 1. J equals 1, j equals 2, j equals 3. And now for each state, we compute this delta here. But we also compute this AT of 1, which is simply a pointer backwards to the state that created our maximum, right? We say, which are the possible states that we could have in the previous state? And then for each of these states, how can we reach this state, which was the maximum way to reach this one here, and then we take just the max of all these. But we also store, right, a back pointer and say, hey, I came from this, right? The probability of reaching that state times probability to reach that state times observing what I observed is maximum. So I store the argmax in this node here, right? I remember, okay, my previous state was again state 1, right? That's the whole idea. Because then if I do that, I can just go to the very end and then trace back, right? And then just take all the maximum in all the little states. This is the whole algorithm written in math. So I initialize this, right? These delta values are initialized, and I also this psi. Actually, this should be A, right? This is wrong. This is sometimes it's called psi and sometimes it's called A, right? So again, sorry for the confusion. It's an A, but here it's a psi. So you have initialized values here, right? These are given already because I know these states and I know the observation model, right? This means this is just multiplying my pi's here. These pi's are just probabilities of reaching the state in the very beginning. And for every state here, I can then multiply that with my observation that I had in the very first state, right? And then I do this here. I compute recursively these values here. Yeah, this is very similar to what you had before, just with forward backward, right? We can do this with these deltas are very similar to the alphas and betas, and I also store the argmax in every state, right? For every what I said, I store where this came from, and then in the very end, once I reach the end, I just take the probability that maximizes the last state, and I trace back, right? For this xn here, the most likely last state is of course just the one that maximizes the last state, right? If this was the last variable here, I just take the one with the state with the most likely delta here, with the highest delta, and then just go back. Like for every new x star, I just take a of xn plus 1, so I just go backwards. This is the second kind of thing we can do with HMMs, and the third thing is the observation is to find the parameters, right? So we have again observation sequence, and now this is the hardest problem. Now we don't know the A's, we don't know the P's, we don't know the model itself, right? We model this still as discrete variables, but the details about these models we don't know, right? And the problem here is that this cannot be solved in closed form. We need an iterative algorithm, and the algorithm we do for that is the EM algorithm, expectation maximization. And for the particular case of HMMs, this algorithm is called Baum-Welch. I'm giving here like a first glimpse of expectation maximization. There will be a whole lecture on that. So expectation maximization is a very general algorithm that has been applied in many other contexts in machine learning. Particularly for HMMs, there's a special form of that algorithm. But to understand EM much better, we need much more, like say, insights from other sides. So it's not this does not explain everything you need for EM, right? It gives you an idea of what EM does, but we will have a much more detailed discussion on EM, also on a theoretical side, in some later lecture. For the moment, we just say our objective function is find the model parameters, and what we can do is we can now train an HMM to recognize a sequence of inputs, and we can also train an HMM to generate sequences of inputs, right? Imagine you have your A and you have your pi's, then you can of course use that to sample, right? You have a graph, you can then say, what's the probability of reaching one state from the other state? You sample from that and you create new observations, so it's really a way of sampling new things, generate new sequences from that HMM. So the two steps are E and M. In E step, what we do is we find the best state sequence given the parameters. And M, we do find the parameters using the state sequence. That means we have this iteratively, this alternating things, right? So we start with some observations, with some initial guess of observations, and in every EM round, we refine that and say, given the current estimate of our parameters here, what is the most likely next set of parameters? So here in the E step, we assume we know already some kind of start values, right? This is also an important notion of EM, right? EM always needs initialization. It cannot start from scratch. So, and it's very important to have this right? Of course, the better my initial estimate is of our parameters, the better is the end. But of course, this is what we don't want, right? This is like this kind of trade-off. If we know PA and phi already, then we don't need to do this algorithm all over. But yeah, so if we don't know anything of this, then EM will converge probably very slowly, or even not converge to something we could use, right? But again, all these details I will talk later about. So for the moment, we say, okay, we know some kind of representation of this PA and phi. We say call this theta old, which is just from the previous estimation round now. Now, we define the posterior probability of being in state I at step k, which is this gamma. Now we had alpha, beta, now we use gamma here. Gamma of x, this should be t, right? xt is the probability of xt given z. And from that, we can directly say this is nothing else than alpha times beta and normalized, right? This is from the way we define gamma, we can already use our formulation for alpha and beta and plug this in, and we say that gamma equals the product of alpha and beta. I think this is the our summary already of the algorithm itself. Again, this is just very roughly, very like high level, and let's say suited for the case of an HMM. It's just to show you that it is easy to do that with HMMs because we have these gamma values and we have also these values here. So what we do is here we have these gamma values. We also define these psi values, which are probability transitions, or state transitions, right? What's the probability of these two states jointly, right? There's a slightly different notion here. We can then express this psi as, again, as alpha and beta, and our this is the observation model, this is the state transition, and we normalize that, right? So we have this whole thing here. And the whole thing that we need to compute in every EM step is the so-called expected complete data log likelihood. And we'll later see what this is, right? Why this is called like that, what is this term here? The whole thing right now is just for you to know that it is something like a marginalization, right? We have this probability here, and it's a joint. It's a joint of the hidden states, x, which we don't know, and the observations, z, given our parameters, right? This whole thing is a probability distribution. We do this in log space because it's more efficient. And we compute, instead of marginalizing out our state x here, which we don't know, we take the expectation of that. An expectation is nothing else than the sum of our all states of that x thing, of this here, times the probability that we reach that state x, right? And this is this is based on our previous parameters here, right? So this whole thing is nothing else than an expectation overall of the complete data log likelihood, right? Again, we will have this in more detail later. Yes?
In the previous slide, does the initialization step affect the convergence?
Yes. Yes.
About that initialization?
Yes. Yes. So again, yeah, the question was if the initialization changes the convergence, and yes, it does a lot, of course. There you have to find good ways of finding good initialization. And what we can do is, I think we'll have this also later, we can, what people usually, sometimes do in general is they use k-means, which is a bit better algorithm that converges a bit better in the beginning, and then the outcome of k-means can then be plugged into EM. There's other techniques to do that, but this is definitely a problem, right? That's right. The initialization of these parameters, this is quite important. Yeah, okay, and then in the M step, we just do these kind of operations here. Again, I'm not going into details. I cannot guarantee that all these things are properly correct. I have to check this again because, again, I did this in 2 books. And so don't pay too much attention onto this. The only thing is, what this should give you is that there's a simple operation which is basically taking averages, right? You take expectations over this thing here and you average over all possible states, right? So these are the 2 steps that you do in the M step. and then you have a new Q, right? You have a new set of pi and A they go again into this theta here. So the new theta here is then replaced by a theta old, and in the next E step you compute this thing again here, right? So and the whole thing is done iteratively until the likelihood does not increase anymore. You have a convergence criterion that says, hey, this likelihood thing here, right, doesn't change it anymore, and I stop and say, now I'm done. You can define this as convergence. To summarize, this algorithm is like this here. We start with an initial estimate. For example, we can uniformly do this, or we can do this with k-means, that's what I said already. So we have k-means for this parameter here, and we initialize these values like this. Then we compute the E and the M step, right? We have this Q function here, right? The expected complete data log likelihood, the Q function, which is a function of an old kind of parameter set and a new set here. And then we maximize that Q with respect to theta, right? You find a theta that maximizes that Q, and that theta is then plugged into the next E step as a theta old, and we find another theta new, and so on. So we iterate EM until convergence. In each iteration, 1 full application of the forward-backward algorithm is performed. That's important, right? We have to do this inference, it's called the inference step of the HMM in every iteration of EM, which makes it, of course, a little bit efficient. We have to not only do this once, but for every new parameter set, of course, we have to then re-estimate the whole HMM again, right? We have a new estimate of thetas, then we do forward-backward again. In some end we do this until convergence. The result gives only a local optimum. This is important to know that we're not guaranteed that this likelihood that we get is the global optimum. And if we're not happy with that, then we have to initialize this with different terms and then hope that at some point we get some better estimate, right? So that means if you want to find other local optima, that's what I said, we have to then start the same algorithm with new initialization. One last point about the scaling thing. This, I think I said this already in the case of the max-sum algorithm. Here we have the same problem here. We have products over probabilities of something, and these probabilities can be very small. If I multiply them all up, then the whole product will be very small. And what we do here is we convert this whole thing into log space. The problem here is we don't maximize here. We don't have the max product algorithm, which we just turn into a max sum algorithm. But instead we have sums of products. And these sums are not so easy to handle with logarithms. Like logarithms don't like sums. And so the solution here is in every step, in every EM step, we can then rescale, normalize the probability during computation. So instead of alphas, we use alpha hat, where we just normalize alpha with the joint here, which is given. Okay, this is just a note. Now let's summarize the second thing also. HMMs are a way to model sequential data. So we have seen this already, how we can represent this sequential data with HMMs. We assume discrete states. We have 3 possible operations that we can do with HMMs. First of all, we can compute the data likelihood, right? How likely is it to measure what we actually measured? We can compute the most likely state sequence. This is the Viterbi algorithm that does that. And we can find optimal model parameters given observation, right? We only have an observation sequence and would like to find the most likely optimal, in a sense, parameters for that model. Then scaling is important. And and in general, we say that HMMs are very widely used. Particularly, they have been used very often in speech recognition, where every state is a state in a speech, for example, in in an utterance, for example. Yeah, this is lecture of the day. Thank you.